Our data is about sales of shampoo for 3 years, which contain 36 observations. This data has increasing trend over time. It do not have seasonal trend. ARIMA is known as Autoregressive Integrated Moving Average that deals with non-seasonal data. It uses regression models that use lag values of the dependent variables or random disturbance as explanatory variable. It consists of 4 stages: tentative identification, parameter estimation, diagnostic checking, and forecasting. For tentative identification, there are 2 parts, which are stationary checking and model identification. The reason we use ARIMA for this data is because this data is not seasonal, but it has trend pattern. Before we proceed with the forecasting using ARIMA, make sure you have installed Forecast and Fit AR package. Now we start by importing the data into RStudio. The data that we are going to use today is the sales of shampoo per month for 3 years. It has 36 observations. And we proceed to the next step. First, we call for library forecast. Then we plot the data like so we can examine whether the data is seasonal or non-seasonal, or maybe if the data has a trend. As we can see in this graph, the data is non-seasonal, but it has an increasing trend which we are going to remove later. Then we are going to examine if the moving average model in this data is stationary by using autocorrelation function. This function will later give us a graph that shows us the time lag versus ACF. As shown in the graph, the time lag takes a while until they reach 0, so this tells us that the MA model is not stationary. Same goes with autoregressive model. We use partial autocorrelation function to see if the AR model if it's stationary or not, and it will give us the following graph. The graph will almost be like the graph represented in MA model, but this time it's between time lag and partial ACF. The following graph also shows that the AR model is not stationary. When the MA model and the AR model is not stationary, the data need to undergo differencing process. We are now moving to the next stage where we are going to remove the trend component in this data by differencing. But first, we need to know how many times we need to do this process. So we are going to use the ANDIF function like so, and we can see that we only need to do it one time. Next, we use the diff function for differencing the data to give us a new set of data. We then plot the new set of data and have the following graph. As shown in this graph, there is no more trend in the data. This confirms that the ME and AR models are now stationary. Next, we are going to use ACF and PACF functions again to determine the models for ARIMA. Using ACF function in MA model, it will give us a graph like so. The blue dotted line here represents a boundary. The number of time lag that exceeds the boundary will give us the number of MA models that we are going to use later. In this case, there are 2 time lag that exceeds the boundary, so they will be represented by MA1 and MA2. For AR model, we use PACF function to have the following graph. The next step is also similar where we detect the number of time lag that exceeds the blue boundary. In this case, we only have 1, so it will be represented by AR1. So now we have a total of 5 models in ARIMA: MA1, MA2, AR1, ARIMA 111, ARIMA 112. Later, we are going to see which model will fit best with our data. For this, we use ARIMA function for each of the models that we discovered before. The delta in this equation will be constant because by default, the ARIMA function sets the delta to 0. The output for each of the models that we tested will give us the coefficient AIC, AICC, BIC, and sigma squared. We tabulate all of these for each model to make it easier for us to compare each of them. To find a model that fits best with the data, the model should give us the lowest value for all of the values mentioned before. Based on this table, ARIMA 112 has the lowest value for the coefficient AIC, AICC, and BIC. MA2 has the lowest value for sigma squared. However, we choose ARIMA 112 to be the best model that has the best fit for the data, because it has the lowest value for 3 out of the 4 components. However, we still need to check whether our model choice is true or not. So we use auto.arima function to give us the best fit model in this data. And the best model is ARIMA 111. This leads us to question why is ARIMA 111 be the best fit model when ARIMA 112 has lowest values for all of the components? The answer is that the distribution of the residuals in ARIMA 111 fits better to normal distribution than ARIMA 112. To prove, we use check residual function for both models to obtain the graph for the residuals. ARIMA 112 has a pit in the middle which will not give a good fit to a normal distribution, while ARIMA 111 fits a lot better. For the next stage, we will call out fit AR package. Then we will use the Leung box Q-test to obtain the Q and P values. We later use the values to test whether the model is adequate for this data. A model is adequate for the data when the value of P is higher than 0.05. The P value obtained later is then plotted into a graph like so. As we can see, almost all of them is higher than 0.05, so we can say that ARIMA 111 model is adequate for this data. Next, we use QQ-norm and QQ-line function to test whether the residuals from our model are normally distributed. It is considered normally distributed if the residuals are not scattered randomly and they sit nicely in a straight line. Based on this graph, we can confirm that the residuals are normally distributed since they followed the criteria we mentioned before. Finally, we are going to forecast the future sales of shampoo by using autoplot forecast function. The function will give us the following graph. The blue regions indicates the interval for the future sales. The darker shade shows interval for 95% and the lighter shade shows interval for 80%.